Hello, everyone. Welcome to our Tuesday, March 2nd live session. We are so excited to have you. My name is Matthew. I am one of the astronomy course staff and instructors for our Coursera classes. I want to welcome you all today and remind everyone that you can ask questions in the chat. Please ask them only one time. We will grab them from the chat and ask them on here. We skip around a bit to try and give a variety of people a chance to ask questions and to get a variety of topics. And we keep it at an introductory level so that everybody can participate and understand. I'm going to hand this, one more thing is we also have a follow-up live session on Twitch today for subscribers. Anyone can watch. Subscribers can ask questions. It'll be right after this on our Twitch Teach Astronomy channel. I will hand this over to Chris, and you can say welcome, and then we'll get started with questions.
Okay, well, welcome everyone to another live Q&A session for our online courses, and I'm sure there's plenty to talk about, so I'm ready for your questions.
Excellent. Ayush says, it has kind of a two-part question, so I'll pose the first one. I recently heard that scientists have decoded how Mars might have lost its atmosphere, and they say solar winds might be the cause. What can you tell us about this?
That is one component. I don't think this is a solved issue. The MAVEN satellite was designed, a Mars orbiter that was designed to make detailed measurements of a kind that hadn't been made before to partly answer this question. So over time, we know that the Martian atmosphere has thinned out and that Mars was warmer and wetter in the past. The atmosphere was thick enough, the heat trapping of the carbon dioxide was sufficient to have liquid water on the surface. We know that. There's lots of evidence for that, but that's not the case now. So Mars has lost its atmosphere. Solar wind is a contributing factor, but really the most significant piece of Mars losing its atmosphere is it's a small planet. And so the gravity that can hold molecules in the atmosphere is a function of the temperature, so the radiation from the sun, which creates a mean velocity for those molecules, and that's just compared to the escape velocity. And so given that Mars was warmer in the past, the atmosphere had a higher temperature, so the velocity of the molecules was higher, and given the weak gravity, the atmosphere was very slowly leaking off into space. And then, of course, you lose the compounding effect of the greenhouse heating from the carbon dioxide. So Mars, being 50% further from the sun than the Earth, would just chill out and have a thin atmosphere and a frozen surface. So it's the solar wind is a contributing factor. The solar wind is essentially high energy particles that ablate or sort of boil off, if you like, some part of the Martian atmosphere. So it's probably contributing of that factor and a couple of other factors.
And then the follow-up question is, could something like that happen on Earth? Could we lose our atmosphere? Could the solar wind blow our atmosphere away? Is it a danger to us?
So the solar wind obviously is stronger. So we're 50% closer to Mars. That means the sort of net effect, given inverse square law, is just over 2 times more. So the solar wind is just over 2 times stronger at the Earth's distance than it is at Mars' distance. But that's countermanded by the fact that the mass of the Earth is 4 times more than Mars. And so the Earth's ability to hold its atmosphere is still stronger, even taking into account the stronger solar wind. So there is no particular evidence that the Earth's atmosphere is changing on any small time scale or even long time scale that we can measure.
Excellent. Thank you very much. Sanchita says, my question is, if humans were to settle on Mars, will they have to live in tunnels and tents and wear heavy spacesuits every time they step out of home?
Yes, absolutely. Living on Mars as colonists or even for long term, like 5 or 10 years, will be very challenging. The radiation environment is intense because the atmosphere is so thin, and so the level of cellular damage and mutations to human genetic material would be substantial if you weren't heavily shielded. And it does mean quite heavy shielding. Now, to get to Mars, you can't be heavily shielded, so the people who go to Mars are going to have to suffer 6 to 8 months of radiation exposure on their way there and on the way back. But on the surface, indeed, habitats will be built that have quite significant shielding from the radiation. They won't be nice bubble domes where everyone just gets to stare off at the Martian landscape. There's two real ways to do that, to create a protective environment. One is to use the Martian soil, the regolith itself, to make building materials. And we've prototyped machinery on the Earth. NASA has models that it can scale up of electrochemical machines that essentially take the regolith and turn it into slump block, and you can just build on top of a dome. You have to create a skeleton structure and then clad it with this material. The alternative is to find an interior cave-like structure that will suffice without so much construction. And we've already identified lava tubes from situations where there was volcanism and geological activity in the past. And so if you found the appropriate lava tube, you could make that into a habitat with hardly any extra work. These lava tubes also exist on the moon, as it turns out, and would also be good habitats for the moon.
Sanchita would also like to know, will those born on the red planet adapt themselves or be able to adapt themselves to the thin atmosphere and less gravity automatically?
Well, people born on Mars in some future colony scenario will of course not deal with the thin atmosphere. They'll be having an artificial atmosphere that's essentially like the Earth's atmosphere, well, maybe with slight modification, but basically the same. So they won't have to adapt to an atmosphere. It will be a very clean atmosphere, so it'll be clean of pollutants and dust particles and so on. So it means that people that living on Mars and used to this ultra pure atmosphere may actually have problems when they come back to Earth and deal with the pollutants and contaminants and particulates that Earth air is full of. So they'll be having very clean air to breathe. The reduced gravity definitely will have an impact, and for someone born on Mars in reduced gravity, it will affect the way they grow. It'll affect their development of their skeleton, their physiology, the internal organs, and the way they settle in the body. Now, not dramatically in one generation. It'll be an adjustment of someone growing up in a strange situation. But over some generations, the human form of people living on Mars and living and dying there and new generations born there will actually start to change on a fairly rapid time scale compared to normal evolutionary processes. And people have actually made models or tried to understand how that might be. The body will become more hairless, the body will become a lot taller and skinnier generally, and other changes are likely to take place.
Excellent. The next question is from Physics Knowledge. Is life possible on exoplanets?
Well, that's the big question that astrobiologists are trying to resolve right now. So currently we know of over 4,000 exoplanets, numbers heading towards 4,500. It pretty much changes every week. And among that number, maybe about 10% are considered to be habitable, which is to say they are planets within a factor of 2 of Earth's mass or size, and they're at a suitable distance from their parent star that liquid water could potentially be on the surfaces. So that's the sort of definition of habitability. We expect that the ingredients for life, which is to say liquid water, carbon-rich material, and a local energy source, sunlight from the star, of course, or as on the Earth, it could be geothermal energy or interior radioactive heating, exists on all these exoplanets. So when you have the ingredients for life, it's quite plausible that you are going to have biology. So without knowing the answer, astrobiologists are really speculating that there are a large number, perhaps 10 million total, habitable worlds just in our galaxy alone. Getting the evidence that they are inhabited by, say, microbes, the most likely life forms, is a very challenging experiment, and that's the next big hurdle in astrobiology. But over the next 5 to 7 years, it's likely that those experiments will be done with telescopes on the Earth, big telescopes being built in space missions, and we may start to know the answer to this question.
The next question from Anastasia. What are the prospects for studying pulsar exoplanets? And why is it necessary for humanity in general if life will never appear on them?
Pulsar exoplanets are a sort of an esoteric niche of the field of exoplanets. Some people forget that although the Nobel Prize was given in 2019 to Michel Mayor and Didier Queloz of the Swiss astronomers who discovered the planet around 51 Peg, a half Jupiter mass planet around a sun-like star, as the first discovery. Nobel Prizes are given for the first discovery of something. It wasn't actually the first exoplanet to be discovered. They published in 1995, but in 1992, based on observations that are actually a few years earlier, Alexander Volskan and Dale Frail, working at the Arecibo Observatory, discovered two planets around a pulsar. Pulsar is a dead star, a collapsed massive star that's a neutron star essentially, and has hot spots that lead to radio emission that pulses because the star is spinning rapidly. So these were completely unanticipated, and when they published it, nobody really knew what to make of these rocky bodies around a pulsar. This pulsar was, I think, Pulsar 1257 plus 12 is its actual RA and DEC number. And subsequently a third planet was found. These planets were confirmed before 1995, so in a sense you could say, why didn't these two gentlemen get the Nobel Prize? It's a good question. Ask it to the Nobel Prize Committee. So these pulsar planets are small. They're 3 or 4 times the size of the Earth, and the third one that was discovered a few years later is actually twice the size of the Moon, and that is still the lowest mass exoplanet known at all, anywhere. And having found pulsar planets back in 1992, people looked for planets around other pulsars, and I think only a handful have been found, so they seem to be rare. People still don't know how pulsar planets get that way, whether they're produced by after the star has died. It's unlikely that they're there at the star's birth, at the beginning of its life, formed in the normal way that exoplanets formed, because the planets probably couldn't survive the supernova explosion that leads to the pulsar. So it's possible and most likely that the planets are formed from debris left over from the supernova explosion. And that makes them rather different from the normal type of exoplanet that most astronomers are finding.
The next question is from Sarah Ravaza. If one is based in an urban area with a lot of light pollution and wants to buy an amateur telescope, what is best, and would infrared help against light pollution?
Well, if you're in a city, it's challenging because, in a sense, this is a sort of fundamental issue at play. Having a more light gathering power, which you have with a telescope compared to your eye or even binoculars, it doesn't buy you that much because you're also collecting more light from the sky. And if the sky is brighter, then the dilution of the astronomical light, which affects its visibility, is just as bad. The telescope does, however, help because it can create sharp images, sharper than the eye can see. So it's not true that the telescope doesn't help you at all. It just doesn't help you as much as you'd think because it's not getting around the brightness of the night sky. And unfortunately, going into longer wavelengths in the infrared doesn't necessarily help either. And that's because urban and city situations are warm situations, and warm ambient buildings and roads and structures create infrared radiation. So the infrared backgrounds in cities are actually worse than in the countryside. So going to the infrared doesn't help either. That's unfortunate. So I guess my best statement would be you're wasting at some level the power of a decent telescope by observing it when in a city. If that's all you can do, I'd say good high-powered binoculars are your best bet, and they're significantly cheaper. You'll see almost as much as you could see with a small telescope. Otherwise, your best bet, of course, is to find a place at the edge of your city. You don't always have to get out of a city by more than 10, 20, 30 miles. If you can find a city, if you're in a city that has some shielding hills or low mountains and you can get just beyond them, then you get quite a lot darker sky. So you really have to work to get away from city lights to see much in the sky these days.
So the interstellar object Oumuamua has been in the news recently because of Avi Loeb's book. And this is not specifically about the book. They would just like the email would just like you to talk about Oumuamua, but perhaps you can talk about why it's been in the news and what it is.
Right. Yeah, we've had some questions about Amumu recently, but I'll recap the basic issue. Amumu is a very unusual extraterrestrial object. It's presumed to be a near-Earth asteroid type object, but it's very elongated, and it's quite dark material. It doesn't reflect much light. And when it was picked up, it was coming in on a very unusual trajectory with very high velocity from further out in the solar system. And so the trajectory and the velocity puzzled astronomers, but even more puzzling was its highly elongated shape. Most rocks in space, asteroids, comets, other forms of debris, they're not always round unless they're big enough that gravity makes them round. But having one that's elongated at a ratio of, say, 8-to-1 or 10-to-1, that's exceptionally unusual, basically unheard of. Now, a fragment of an object could have that elongated shape, so it's not impossible. The Loeb book essentially says that the most plausible explanation for Amumu is that it's an alien artifact, that it was actually created. It's a piece of engineered technology sent by an alien civilization into our solar system. Not clear why, perhaps to track us or to gather data, who knows. He's received a lot of publicity, a fair amount of acclaim, and a fair amount of pushback on this hypothesis, because many astronomers simply feel that is not at all the most plausible explanation for the data. There are puzzling issues for sure about the size and structure of the object and its trajectory, its velocity and path in space, but they do not lead you inevitably and convincingly to the alien artifact hypothesis. That's quite an extreme hypothesis. Of course, Loeb, in his book and in interviews, sort of flips this argument on its head, and he tries to rebut what Carl Sagan said, that extraordinary claims require extraordinary evidence. So he kind of turns this argument on its head and said it's much more extraordinary to explain this without appealing to an alien artifact. He also tries to make another point about astronomy and the culture of theories and how people hold them, and he says that people get far more acclaim and approval for enormously speculative theories about string theory and the early universe and multiple dimensions that are not bolstered by data. So why not make this claim for Oumuamua? It's a kind of contrarian argument. He's at heart a contrarian, but a very smart one. So most astronomers do not accept his hypothesis.
Excellent. The next question is from one of our live participants. How will the samples collected by Perseverance be brought back to Earth?
Yeah, that's an important part of the Perseverance mission. It has within it a canister with cylindrical samples, core samples that have been drilled by the instrument. I don't remember how many, I think it's 8 or 10 maybe. So it's a sort of carousel, if you like, of core samples. The samples are put inside sealed containers that then take out any possibility of contamination. So as soon as the samples have been extracted and put into their initial canister, they're sealed, and so they're preserved, immune from any other contamination that might happen. And then they put in the carousel. The carousel will be left behind on the Martian surface at a preordained location. Of course, it has GPS and ways to tell an upcoming spacecraft exactly where it is, but it'll be somewhere near the Perseverance landing site, of course, in an area that is reasonably easy to traverse or to land on so as not to create a hazard for the spacecraft that will come and collect the samples. And it's an uncertain time scale. It's a multi-stage process whereby Perseverance is going to do this work. It's going to stage these samples, leave them behind when it runs out of power or it reaches the end of its lifetime. And some years after Perseverance has stopped operating, a subsequent mission will come back to that location and pick up the samples. And it's possible that other missions will have come in the meantime, so there may be more than one set of samples to retrieve at that point. So NASA is working a few steps ahead in this chain of reasoning, and they haven't yet built or funded even the mission that's going to bring the samples back, but the time scale is probably about 10 years from now.
The next question is from Kashu Akella, who sent an email. I've read that I've read that particular types of stars might be able to turn into planets, like brown dwarfs. Are they considered planets, and can a star turn into a planet?
That's a good question. There tends to be a strict demarcation between planets and stars. The simplest definitional demarcation is that stars are hot balls of gas, plasma, which create their own energy source in their cores from fusion power. That's the definition of a star, any star. Different types of fusion reaction in different stars at different stages of their lives. A planet is an object that does not create its own energy. It has no fusion, so it can't be that hot, and doesn't create its own light, only shines by reflected light. And it is presumed to have two components, a rocky core and a gaseous envelope. The relative proportions of the rocky core and the envelope can be quite different. There are obviously rocky planets with very thin atmospheres like Mars, and there are planets like Jupiter where most of the mass is in the gaseous envelope of hydrogen and helium, and there's a rocky core deep inside it, but it's quite small in mass. So those are the definitions. Now, a star can't turn into a planet because a star is by definition massive enough to create an energy source of fusion, and the center of that star is just a very hot plasma. There's no rocky material, and in fact no solid material could survive. It will be vaporized and turned into a plasma too. So that's a basic reason why a star can't turn into a planet. Equally, a planet can't turn into a star because planets, almost by definition, have far too little mass to ever ignite a fusion process in their cores. So the interesting thing is the demarcation. 8% of the mass of the Sun is the boundary between a star and a substellar object. So below that boundary line, you have a brown dwarf. You have an object where there's heat because there's pressure on the gas, and so the gas has a high temperature, but there's no extra energy released from fusion reactions. So brown dwarfs are below the star boundary, but they're not planets either. And then there's this sort of nebulous no man's land between 8% of the mass of the Sun and a factor of 10 smaller than that, where you get the most massive planet. The most massive planets that have yet been identified beyond the solar system are about 13, maybe 15 times the mass of Jupiter. That seems to be the natural upper limit to a planet. And 8% of the mass of the Sun is the lower limit to the mass of a star. So the intermediate middle ground is the region of brown dwarfs.
Thank you. The next question is from Junaid Atta. If Hawking radiation is true, then what happens at the end of the life of a black hole?
The end of a black hole's life, if Hawking's theory and idea is correct, is that the black hole evaporates and it disappears. And it actually does so in an interesting way, because the amount of Hawking radiation as the black hole evaporates and shrinks increases. The rate of the Hawking radiation increases and its temperature increases. And so it's an accelerating process. And so as a black hole evaporates towards nothing, this is a crescendo of evaporation and energy release until the black hole just fizzes out of existence. Now, the process itself, the whole process, takes an enormously long time for a star like the Sun. But once it's ablated or evaporated down to a very small object, then the last part is quite quick. We haven't been able to confirm any of this because we've not seen Hawking radiation or black hole evaporation. But if the theory is correct, then black holes are not eternal.
Paradigm Shift asks, in an exposure from the NASA Micro Observatory, could a shooting star explain what appears as a bright line in the image?
Definitely. So NASA's Micro Observatory, which is referenced in the question, is a nice NASA project of it's a robotic telescope array actually, which is open to the public or people can request observations. I've used it in classes here at the University of Arizona, for example. So you can control these telescopes or give them orders and take images, and the images get returned to you over the internet or by email. And it's a very nice teaching resource or outreach resource. Now, these telescopes are not very big, and so they can't see very deep. So the number of objects that can be observed essentially includes, the planets, of course, the brightest star clusters and the brightest Messier objects, for example. If the field size is quite significant, though, the odds of capturing a shooting star or a streaking object are very low on any individual frame, but it's certainly possible that they can be captured. And so seeing one in a micro-observatory frame is very lucky and very unusual, but it definitely can happen.
And it could also be a satellite, I would assume.
Right.
So, yeah. And the next question is Red Unleasher would like to know, could you please elaborate on what exactly ferrite materials are?
Ferrite materials are essentially iron minerals, iron-based minerals. And so they are all the minerals that involve combinations of iron, magnesium, silicon, oxygen, and carbon in various combinations. So there are many ferrite minerals, dozens, perhaps hundreds actually. And these are normal minerals that are found in the crust and the mantle of rocky planets or objects formed out of rock in the solar system. We have ferrites on the Earth, of course. They've been found in the Moon. They are almost certainly on Mars too, or any rocky planet. They are magnetic minerals, and so certain ferrites, of course, can show influence of magnetic fields. If they melt and solidify in the presence of a magnetic field, then the crystals and the grains align, the iron crystals align, and so ferrites can also show the influence of a magnetic field or the magnetic field reversal over time if you can find strata that include ferrites over a period of time.
The next question is from Tian Kuto's on with us live. How do neutrinos form, and can they be considered dark matter?
Neutrinos are a highly abundant fundamental particle. There are as many neutrinos, if not more, as there are protons, neutrons, and electrons in the universe. So they're a ubiquitous fundamental particle, and they are generated fairly readily in nuclear reactions. The process of fusion in the sun creates antineutrinos, and neutrinos come from nuclear reactions as well. And so they are ubiquitous particles, and because there are as many of them as there are protons, electrons, and neutrons, it was naturally wondered whether or not the neutrino might account for dark matter. Neutrinos interact very weakly with radiation or matter, and that's why maybe they do have some of the attributes we give to dark matter. It all depends on their mass. For neutrinos to be dark matter, they actually have to have quite significant mass. Now we know that neutrinos are not massless. They travel at nearly the speed of light, but they're not massless. But current observations don't tell us the actual mass of the neutrino. Neutrinos oscillate between the three different families or flavors of neutrino. There are normal neutrinos, the electron neutrino basically, and then the muon neutrino, and then the tau neutrino going up in mass. So we know the relative masses, or the difference in the squares of the masses, from neutrino oscillations, which have now been observed in physics experiments. But we don't get the absolute mass of any of the neutrino flavors. Indirect arguments show that the neutrino mass is likely to be too small for it to account for dark matter. That's one reason. The second reason is that neutrinos in cosmology have the effect of erasing small-scale structures in the way they stream in the early universe. And that would go against the idea of how structure in the universe formed from small structures turning into larger structures. So for these two reasons, we don't think neutrinos are the dark matter.
So the next question is from Hernan Reyes, and I'm going to divide it into sort of two parts. The first part of it is that Perseverance has the Perseverance mission to Mars has everybody quite excited about finding traces of life way back in the past on Mars, and the mission will be looking for biosignatures. So can you talk about what a biosignature is and what biosignatures Perseverance might be looking for on Mars?
Sure. A biosignature is a general term. It's a term in biology that means something slightly different, but as used by astronomers, it means chemical traces that indicate biology at work. So it's indirect indication of biology. It's not looking at fossils, it's not looking at moving creatures and taking pictures of them. It's looking for traces, chemical traces that indicate biology is present or was present. The Perseverance rover has some fairly sophisticated instruments. It will be able to drill, take samples, look very closely at rock. And so one possible biosignature that Perseverance might find with its incredible cameras are it might be able to see microfossils. And so there were fossils on the Earth 3.6, 3.4 billion years ago that are inclusions in the rock that morphologically are very hard to just explain as normal crystal formations. And so it's possible that it'll see microfossils. And the most extreme and wonderful version of this would be to see stromatolites, which are bacterial mats, and the Earth had bacterial mats going back at least 3 billion years. That would be spectacular. That's quite unlikely, however, that there are stromatolites on Mars in the Jezero crater. So it may find more subtle morphological forms of life, but more typically it's going to use mass spectrometry to look at the chemicals in a rock, either by reflectance spectroscopy or by vaporizing the material, which it has the ability to do, and sampling the material directly in a gas chromatometer. So these are just looking at the chemicals and saying which of these chemicals is most likely to be associated with biology.
All right, so then the real question is, if and when Earthlings send an exploratory mission to Titan, what kind of biosignatures can we possibly plan to look for when we have no idea what life form could evolve there, since it's not water-based and it would have to be based on methane and ethane? How can we detect a form of life that we have no solid predictions for?
Right. So the Titan mission, which will include the Dragonfly technology, essentially a drone technology able to sample the liquid in the Titan lakes and material on the surface too, that is designed to look for biomarkers, also to see if there's a possibility of conventional or strange forms of life on Titan. So both with Perseverance, which does mass spectrometry, and with Dragonfly, which is doing mass spectrometry, it's important to know what the mass spectrometer can and can't do. The mass spectrometer is a very sensitive way of segregating out different chemical ingredients by their mass and indirectly their structure, and saying what chemical ingredients are present in a soil sample or a rock sample or a liquid sample. But mass spectrometry on its own does not tell you the function of a particular chemical that you might find. And also, it doesn't always resolve the ambiguity between two different chemical symbols for an ingredient, a molecule, that have different functional forms or do different things functionally in a sample or in biology. So it can find things like amino acids, simple amino acids, or simple lipid molecules, fats, the basics of acids and bases in biology. But these are at the level of 20, 30, 40, or 50 different atoms arranged in particular ways. Once the molecules get complex enough, mass spectrometry stops being able to very efficiently sift the possibilities. And it sometimes cannot uniquely identify a molecule. Also bear in mind that when it comes to the Titan mission, a large amount of miniaturization has to go on. The probe on Titan has to be much less massive than the probe that was sent to Mars. And so the mass spectrometer is a highly miniaturized version of a mass spectrometer that we would use in a lab on the Earth, maybe 100 times smaller and less massive. And that's pretty challenging. So this is not a state-of-the-art mass spectrometer as we would understand it on the Earth. It's fairly limited in what it can do. And so its ability to diagnose biology is also limited. It's a fairly indirect process. It's going to see a slew of chemical ingredients. It's going to indicate mostly what they are when they're simple. When they're complex, it gets more ambiguous. And that whole package, that whole list, and their concentrations and proximity to each other is going to have to be a big jigsaw puzzle that people put together to deduce whether this might be associated with biology.
Thank you very much. The next question is from Jorge Kitrosser. Are there any ongoing solar sail projects that are either in space or to be launched soon that you know of?
I'm not aware of any that are coming soon, but there are solar sail projects that are still underway and in development. There were a couple of spectacular solar sail failures in the last decade that set back private enterprises that were planning to do this. One of them was the one that Andrewian is involved in, the widow of Carl Sagan, who has been heavily involved in visionary space projects. And the Russians had a solar sail that also failed. So there have been some failures, but people have not given up on this technology. I'm sure you know that Breakthrough Starshot, the attempt to send nanobots to the Proxima Centauri system, is based on solar sails, which are used to accelerate their nanobots to a fraction of light speed using powerful lasers beaming up energy from Earth to the solar sail. So there's a lot of solar sail development still ongoing, but the planned tests are quite modest in size. These are just solar sails of tens of square meters in size, and so to do something ambitious, you actually have to test and deploy solar sails that are substantially bigger than this. So this development, this R&D effort, is actually proceeding quite slowly.
And it seems that LightSail 2, that was launched by the Planetary Society, is up and still functional. So it's been up for 609 days, apparently. Okay. David Gold would like to know, what is the significance of the Zodiac in the in astronomy today?
In astronomy today, it just has purely historical value. The Zodiac comes from the Greek and then Latin for zoo of animals, and so the Zodiac is, in the present day, the constellations that run around the ecliptic. So the ecliptic is the path of the sun as seen in the sky. Well, of course, when the sun's out, you can't see the stars, but 12 hours away, or on the opposite side of the sky from the sun, those constellations that are on the path of the sun are the circle of the Zodiac. Those are the constellations that form the normal constellations in the horoscope, and so they've been prominent through history. They're associated with classic Greek and Roman myths and legends. Now, back in the day when they were first demarcated, there were actually 13 constellations along the ecliptic that formed the Zodiac, and over time the 13th was lost, leaving us with the 12 we see today.
The next question is from Walter, who asks, are cosmology, philosophy, and religion linked in any way?
Cosmology, philosophy was the second one, and religion, yes.
Correct, yeah, cosmology, philosophy, and religion.
Definitely, indirectly, but significantly. Cosmology and philosophy are definitely linked, because cosmology is the study of the universe as a whole entity, as a whole thing, the history of the universe and everything in it. And at some point it shades into philosophy, because we don't know what caused the Big Bang. We don't know why the universe came into being in this extraordinary event called the Big Bang. We don't know necessarily exactly how it will end. We don't know why the universe has exact properties that we observe it to have. And so when you're asking these questions, you're actually getting close to some philosophical questions. You're also obviously getting close to some religious questions, because religion, not just organized religion as it relates to how we might live our lives and so on, also deals with these very large issues of why we exist at all, and why humanity exists, and where the universe and the earth came from. Cosmology tries to answer these questions, but it leaves the door open for religion, because cosmology, as I mentioned, has no explanation for the source of the Big Bang, the origin of the Big Bang, or what happened before the Big Bang. So there is a dialogue between philosophy and cosmology, definitely, because it's asking deep and sometimes unanswerable questions, and that creates a dialogue with religion too.
The next question is from Lysos. Are there any objects in space besides Andromeda that are blue-shifted?
Good question. Yes, there are a few. The local group is the small set of galaxies that we're a part of. The two largest members by far are us and the Andromeda galaxy, almost a sister galaxy to ours. Next to Andromeda, which is M31, is M33, which is a smaller galaxy. And then the Milky Way and Andromeda each have a set of about 12 or 15 satellites, dwarf galaxies. And so these dwarf galaxies are typically bound to the massive galaxies in the local group and are orbiting them. And if you measure the Doppler shift of the dwarf galaxies in the local group, a number of them, I don't remember the exact number, but it's more than a few, do actually have blue shifts, because their instantaneous velocities, given that they're bound to the Milky Way, will, of course, half of them will show blue shifts and half of them will show red shifts. So these galaxies showing blue shifts because they're not partaking of the general cosmic expansion, because they're bound by gravity to the Milky Way.
The next question is from Nikki Parker. Does a binary millisecond pulsar or a black widow pulsar eventually become a black hole?
No, unless there's a merger event. So a pulsar, which is a neutron star with hotspots and blemishes that lead to radio emission, the neutron star is an end state of a star. Its mass is defined at that point, and so its mass is somewhere between 1 and 3.5 times the mass of the sun as the remnant, and that defines it as a neutron star, and that's not going to change. In a binary system, however, because of the ability of gravitational radiation to take energy from the binary system, if you have two compact objects in a binary system, then eventually their orbits will decay with the energy being carried away by gravity waves, and they will coalesce. And at that point, depending on the mass of the companion, a neutron star could go over the edge of 3.5 solar masses and so become a black hole. So yes, in an evolving binary system, it's possible for a neutron star to become a black hole.
Vishak would like to know, how do you think the proposed 100-kilometer collider would change the current understanding of subatomic particles?
So the accelerator that the question is asking about is the successor to the Large Hadron Collider. So the Europeans are doing their very best to squeeze all the science they can out of Large Hadron Collider. They essentially have several times upgraded the superconducting magnets that accelerate or that bend the particles in their orbits and let the accelerator get high energy, but they're almost at the limit of what they can do at CERN with the Large Hadron Collider. And the results, to be honest, apart from the incredible and important discovery of the Higgs particle, have been a little disappointing. Physicists have not seen signs of supersymmetry. They've not seen signs of shadow matter or a slew of new particles at these higher energies that might inform them for changes to the standard model of particle physics. And they just feel that they need substantially more energy. And with everything every possible benefit gained from the Large Hadron Collider, you have to go bigger. And so they're going 3 or 4 times bigger in size and then maybe 2 orders of magnitude higher in energy with their proposed new super collider. I forget what the acronym for this new project is. It's had a design study. There's been quite extensive design work and engineering studies of this. They've already put in an initial funding request to start preparing the groundwork for it. This is a project that will be enormously expensive, tens of billions of dollars. I'm not quite sure how many, and probably they aren't either. And it would take 15, maybe 20 years to construct, and it might be the largest accelerator we'll ever be able to build. And even then, it's not guaranteed that it's going to see new physics, but it would represent a substantial leap beyond the Large Hadron Collider, and so it would be very, very unusual in the history of high energy physics if it didn't see substantially new phenomena.
The next question is from Elia. Can you see, so graphene is kind of a new super material that everybody is excited about. Can you see graphene being used in spacecraft in any way, and what are the ways that it might be used?
Yes, I mean, it's a very interesting material. It's obviously a carbon allotrope. It has very interesting properties of strength, flexibility, conductivity. It's really a very promising material. It's not easy to make in quantity, and so it's hard to imagine large structures, large space structures or vehicles made out of graphene. But it definitely could have a role in the space program just because of these very unusual properties that it has. So I expected to see it appearing as components in spacecraft or in spacesuits, for example, sort of very futuristic versions of spacesuits.
Aman would like to know if what is the best example that can explain the difference between continuum and discrete aspects of space?
Well, there's no evidence that space is discrete at this point. So general relativity is our theory of space-time, and that theory of space-time treats space-time as something that mathematicians call a manifold. And actually the definition of a manifold is a continuous structure. It's a continuous, it can be multidimensional, it can be definitely curved, but it is not a discrete structure, it's a continuous structure. And in fact, calculations in general relativity essentially have to assume that it's a continuous medium. Otherwise, these calculations using sort of differential geometry simply don't work. So general relativity is sort of predicated on continuous space, not discrete space. It is speculated, however, since general relativity is not the ultimate and final theory of gravity, that an eventual theory of gravity may accommodate discrete space in the quantized sense. But we don't know what that theory will look like yet. And it's not well developed at all at the level that general relativity is. So at the moment, we're really very uncertain as to what any theory of discrete space might look like.
The next question is from Ellensburg. Has anybody ever observed gravitational lensing using a telescope on Earth or a radio telescope?
So gravitational lensing, yes, absolutely. So lensing is easily seen with the Hubble Space Telescope and in the sharp imaging of space, but plenty of gravitational lensing has been seen from Earth-based telescopes. In fact, the first gravitational lens, which is the double quasar, was discovered in 1979 with observations right here at Steward Observatory in the multiple mirror telescope before it had multiple mirrors. And so, yes, that was 1979, and since then, many examples of gravitational lensing, lens quasars or lens galaxy arcs, have been seen from the ground, and it's not quite as easy to do as it is from space, but it's been done hundreds of times. There was a second part of the question. And radio, yes. So the traditional gravitational lensing involves optical light, but mass bends light. It bends radiation of any kind, and so in general relativity, radio waves can be lensed or bent or magnified or demagnified just as well as light. And so yes, radio astronomers have seen gravitational lensing. They've seen Einstein rings in radio waves, but their lensing events typically use quasars, because quasars emit radio waves. Normal galaxies' radio emission is very weak, so you can't see lensing in it. But for active galaxies and quasars, you can.
Elatora would like to know, is there a black hole at the center of every galaxy?
We think so, but that's not been proven. So the theory and the idea is that every galaxy has a black hole, and the black hole mass, we know, in the hundreds of cases we've seen so far, scales with the old stellar mass of a galaxy. So not the entire stellar mass, but the mass of the old stellar population. That correlation is observed over 5 orders of magnitude in mass, which is quite impressive. So that correlation and the fact that galaxies all adhere to it does suggest that the black hole is a ubiquitous phenomenon. However, there are galaxies which are either so small mass that their black holes would be implied to be small and so hard to detect, or they're so far away that our methods simply don't allow us to identify the black hole, where we haven't found a black hole yet. So in a sense, that's a matter of observational selection rather than the fact that the black holes are not there.
There is somebody who just joined our class, so welcome to you. But they would like to know if we have now detected gravity waves, and if so, do we know the events that they come from? So perhaps you can just kind of give a brief update on where we are with gravity waves.
Right. So gravity waves or gravitational waves were predicted from general relativity back in the 1930s, and for a while it just seemed like there was no way to detect them. The technology to detect them eventually matured, and a very ambitious and incredibly precise project called LIGO, the Laser Interferometric Gravitational Observatory, was constructed in the early part of this century. And it has two separate locations in Louisiana and Washington State. And so these two detectors went online about 7 or 8 years ago, and in 2017 they succeeded in detecting gravity waves for the first time, and the Nobel Prize was awarded for this discovery just a year and a half later. In the intervening time, the LIGO project has been joined by others in Europe. The Virgo collaboration has a gravity wave detector in the Alps, and there are other detectors being built in Japan, Brazil, I think, and India. So the gravity wave game is on. I'd say the number of black hole mergers, because that's the typical gravity wave event, along with neutron star mergers, the number is now over 50. So it's a very substantial sample. And with the current improvements in sensitivity, we can anticipate a gravity wave merger detection pretty much every week.
So the kind of a follow-up question is, can gravitational waves affect the passage of time here on Earth, or I guess anywhere?
In a very indirect way. So gravitational waves are distortions of space-time caused by a mass event, mass changing, merger of black holes, the formation of a black hole, supernova, something in the Big Bang. So in any situation where mass is dynamic and changing with time will generate a disturbance called a gravitational wave that travels at the speed of light in all directions from that source. Now, in principle, when a gravitational wave passes through a region of space or passes over the Earth, let's say, coming from far away, it does not only alter space, but it alters time very subtly. But the level of the alteration of time is at a level that we simply don't have the power to detect. Its alteration of space is already a very challenging experiment. It's a fractional distortion that's, I think, 1 part in 1,000 billion billion, 10 to the minus 21. The distortion or the alteration of time caused by a gravity wave passing through a situation is of similar magnitude, and we do have atomic clocks that are pretty accurate, but there's no way we can detect that yet.
All right, so we are going to have time for about one more question. We have to wrap up a little bit early today. For those of you who are available to join us over on our Twitch channel, we would love to have you come join us for this subscriber stream. Anyone can watch. Subscribers can ask questions, and so we're excited about that. But the final question for today is going to be from Oscar, who would like to know, how is the astronomical research field dealing with open science regulations? What are the plans to provide the community with access to a huge amount of data coming from massive projects?
So it's a good question, and we haven't had that one before. Open science, a very important initiative across all fields that I definitely support. It's the idea of transparency. It's the idea that data should be shared, and that the field, whatever field of science it is, moves forward more rapidly when everyone shares data. It's a core principle of science. But science is a big money game, right? It costs a lot of money to fund scientists to build their expensive toys and detectors, and sometimes the funders put restrictions on the data. Now, the open science has met more headwinds in the biotech and biology areas because of the potential commercial value, for example, of genetics, patenting genes, and so on. Astronomy is in a good position in regard to that because it's a pure science. It's curiosity driven, and there are no obvious commercial implications to most astronomy discoveries. So astronomy has actually been in the vanguard of open science. Astronomers were early and heavy participants in the archive, which is the preprint server that does not have a paywall and often is the first place people find research results. Astronomers with big projects have made their data available routinely to other investigators, including people who weren't part of the collaboration originally. The Hubble Space Telescope, for example, and all the major observatories of NASA and the European Space Agency, they have a proprietary period for data, maybe 6 months, maybe a year, but after that it's open to everyone, literally everyone, not even professional scientists. Anyone can get this data. And most papers that result from this kind of data are also mandated to be made available to people. So the regulatory environment is moving strongly in the direction of open science. funding agencies like NASA and the National Science Foundation are essentially requiring transparency, and that's not just the level of the papers themselves not being behind a paywall, but also the data resources, the archives and the databases being made available, if at all possible, to anyone who's interested. So I'd say open science has a lot of momentum, and astronomers have actually been in the lead on this. That was a good question, different one to answer for the closing question, and good interaction today, a lot of variety in the topics, and we'll be announcing our next 2 sessions soon, and I hope to see some of you on the session that follows. Okay, bye.
Excellent. We'll head over to Twitch for those of you who can join us, and then next week we have our session already scheduled for Wednesday afternoon here in Tucson anyway. So we will see you all next time. Take care.